Okay, strength students. Sorry this didn't get posted by noon, but here we are. So we have, this is similar to what we did today in class, except there's just a few extra steps involved, okay? So we have a rigid bar, ABC, supported by a bronze rod A and an aluminum rod 2 over here. As shown in the figure, a concentrated load P is applied to the free end of the aluminum rod that's down here, okay? And it tells us the material properties, diameters, so we can do areas, blah, blah, blah. Yield strength of the bronze is 50 KSI, yield strength of the aluminum is 36, and we want to figure out what is the load P that we can safely apply to the structure. Okay, so in our last problem we were actually given P. So let's see if we can put this up a little so you guys can see all of it, okay? I want to know the load P. So I have a couple of scenarios. I could put a load P on here and I could have yielding of this aluminum piece, okay? We would have failure. So before we even got loading up to pieces 1 and 2, piece number 3 is gone. So I need to find the load that causes failure by whatever my criteria is of this piece, okay? Well, I could load this piece and it could stay intact, and my force is now working its way up these 2 links or 2 cables. And I could have failure of the bronze or I could have failure of the aluminum. So what I have to do is I have to go back and calculate, okay, given the yield strength of these materials and my factor of safety, I have to find a load which causes failure of this member 1. And then using statics, I can go back and say, oh, well, the P that causes that load is this number. Then I have to assume failure of this aluminum rod. And when I figure out the force in this member that causes that failure, I have to use statics to go back and find P. And then I do the same thing down here. So we're not finding, when I find the force that causes failure in each of these, that's not P for the system, that's just like P, that value P, PL over AE for that member, okay? So it's a step-through process. So again, I like to write down my information, and I like to change all of my units. If I'm in foot, pound, second, I like to be in inches, and pounds or kips, because usually my stresses are in KSI. So we're going to start at the top. We have bronze, we have aluminum, we have aluminum. So my modulus of elasticity for bronze is 15,000 KSI. My modulus of elasticity for the aluminum is 10,000 KSI. And I have aluminum here. Okay. I also am told that I have a diameter of the bronze of 0.375 inches, and I know that area is pi over 4 diameter of bronze squared. The aluminum rod has a diameter, so diameter here of 0.625 inches, and I also know because it's a diameter, it's pi over 4, d squared is my area. And then down here we have an aluminum rod down here, and its diameter is 1 inch, and pi over 4d squared is how I do the area. Okay, the yield strength of bronze, so back over here with bronze, the yield strength, so that's my stress, is 50 KSI. If I don't know that strength is stress, I can look at the units, and those are units of stress. My yield strength for the aluminum is 36 KSI, and we have yield of 36 KSI. Okay, and I want to use a factor of safety of 1.5, so that's how I'm going to end up reducing this yield. I'm also going to simplify these lengths. 12, 24, 36 inches. Okay, lengths 72 inches. 12, 24, 36, 48, so 92 inches. So I have everything now in inches, kips, inches, kips, inches, kips. Okay, and I also have to remember that stress equals force in that member over A. Stress equals E times strain. Strain is change in length over length. And that I have a relationship between the force in each of these members and that load P. So I'm going to start with equilibrium. And I need a free body diagram. And I need some equilibrium equations. So so I can figure out how that force P is distributed. Okay, so if I'm looking down here at this member, then I'm going to look at, here's my load P, and here is the tension in member BD. And if I look at equilibrium, the tension in member BD is all of that force P. It's whatever's in it. Now I'm going to look at the rigid bar, and I have tension BD that's pulling down on it, but that's really just the force P. I have the force in cable at C, and I have the force in cable at A, and I have, well, that's 18 inches, and 2.5 is 30 inches. So I have everything in inches. So now if I sum moments about A, I can get that P times 30 plus FC times 48 equals 0. So I can rewrite this, that P times 30 equals 48 FC. And this is where I can start looking at my ratios. So if I'm looking at P equals 48 over 30 FC. So I get 1.6 FC. Okay, so once I can find FC, if I multiply it by 1.6, that's my load P. Okay, but I also, because I don't know what's limiting, I'm going to write FC in terms of P, so that if something else gives my limiting P, I already have my ratio set up. So I'm going to take the inverse of that, and I get 0.625 P. Okay, so I have my relationship of, I can calculate P given FC, and I can calculate FC given P. So now I'm going to sum forces in the y direction. They equal 0. So I have FA minus P plus FC, which is 0.625 P, because that's really what I'm trying to get, is the relationship between FA and that force P, equals 0. So FA equals, well, P minus 0.625 is 0.375 P. And if I wanted, P is 0.375 inverse, I get 2.667 force in A. So again, I don't know what's limiting, but it's nice to have all of my forces in relation to P and P in relation to forces. Okay. While I'm here, I also just like to go ahead and get that deformation drawn. So I know as I apply a stress in each of these, then I'm going to have some downwards deformation. And I can look at this and I can see that, whoops, I need to circle this too, that if I'm looking at A and B, I have 0.375 P and 0.625 P. So this one has a lot more P than this one, okay? I can also see area-wise, this one has smaller area than this, but modulus of elasticity, so I don't really know if the deformation is going to be straight down and equal, or if it's going to be rotated or rotated. So I'm just going to draw it, and I'm going to rotate this way just because it has the higher force, okay? So the whole system is going to come down. The whole system is going to come down, and we're going to have some deformation from cable A, and we're going to have some deformation from cable C, okay? Which means this point B is coming down from a B to the B prime, okay? And when I look at this tension cable BD, so it's already been displaced by this amount. It has load on it, so it also has a stretch cable BD. So point D goes down to D prime, and the delta of D to D prime has to be delta of B to B prime, so that's just the whole top part rotating, plus the delta as my cable increases. So I'll have to make sure I find both of those, because we are lowering point B just by the downward stretch of these cables, and then there's the rotation, and then we're also lowering D because we have stretch in this cable itself. So we have to recognize the deformation, the change in placement of D is twofold. Okay, twofold. So, but before we can do anything, we've got to get this load P. Got to get this load P. So let's turn this paper over, and I know how P is related to each of my member forces, and I've also been told that each of my member forces has a yield stress, and I have a factor of safety. So the allowable stress I can have is a function of that yield and factor of safety. So if I'm looking at the bronze, and its yield stress is 50 KSI, and I have a factor of safety of 1.5, then the allowable stress for my bronze, okay, the allowable stress for my bronze is going to be 33.33 KSI. If I'm looking at the aluminum, it is 36 KSI divided by 1.5, which that's going to give me 24 KSI. Okay, so let's start with rod 1. If my stress equals force in rod 1 over area of 1, and I know that the allowable stress is 33.33 KSI, that has to equal the force in rod 1, which we were calling force A, divided by the area, pi over 4.375 inches squared. So the most force that I can have in this rod is 33, pi is a number, 4 divided by 375 times, I've somehow already messed up, 33.33, pi over 4 times 0.375 times 0.375 times, and I get the most force I can have is 3.681 kips. So that's the force in A that will cause failure of my whole system, okay? But how does that relate to P? I actually need to know what's happening in P. And I found from equilibrium, okay, that P equals 2.667 FA. So 9.82 kips is what I could put on the system if I were looking at failure of that bar at A. Okay, so now I need to say, well, what is the force that would cause 2 to fail? So I know that stress of 2 is F of 2 over area of 2, and it is made of aluminum, so I have 24 KSI equals the force in bar 2, which we called force B on our statics equations, and then I have pi over 4, and my diameter is 0.625, and I square that, so the largest force I can have in that member B is 24, pi as a number, 4 divided by 0.625 times, 0.625 times, and I get 7.363 kips. So I could have 7.36 kips in that member 2, that this aluminum member over here, before I would have failure of this bar. But how does that get there? Well, I have to go back and look at the relationship with my force P. And I have 1.67 force B. So 1.67 times 7.363. And I get that P can be 11.78 kips. Okay, well, so far, which one limits? This one can only hold 9.82 kips before it fails. This one can hold 11.78 kips before it fails. So far, this is my limiting one. Okay, It can't hold as much. I can't get to 11.78 kips because I will already have failure according to my criteria up here. But now I need to check rod BD. Okay, and it too is a material 2, and I'm going to have a force in BD divided by the area of BD. So it's the same material, so we have 24 KSI equals the force in BD that would cause failure divided by pi over 4, 1 inch squared. So the force in BD that causes failure is 24. Pi is the number 4 divided by times, wow, we can hold 18.85 kips before we have failure. That's just because we increased the diameter from 0.625 to 1. So we got quite a bit more capacity. Okay, and I know it's a 1-to-1 ratio, so P is 18.85 kips. So this P is what will cause failure of that cable BD. This P is what causes failure of the rod number 2, which is on the right. This is the P that causes failure of rod number 1 on the left. So I can see my limiting. This is my limiting member. That's going to be the first to fail. And the most load I can put at P is 9.82. So let's go back and look at our picture here. So P equals 9.82. And if P equals 9.82, well, I can go through the statics again to determine the force in each of these, or I already have them written out. So the tension in BD when P equals 9.82 is 9.82 kips. Okay, so that's the actual tension in that cable based on my limiting load. Okay, and that's what I can use to find my deformation. If I look at FC, 0.625 of load P, well, the maximum I can have is 9.82 kips. So I can see that that is 0.625, 9.82 times 6.1375 kips. Okay, so that's what's going to be in that rod based on that limiting value of P. And then force A, if we look at that, 0.375 P is 0.375 9.82, and it should be 3.681. Okay, 9.82, 0.375 times, and I've messed up my math, and I get 3.68 kips, which I got from the yield stress. Okay, so these are the actual values I can now use for my deformation. And I remember that deformation for C is going to come from that force in rod C, length of C, A of C, E of C. This is going to be force in A, length of A, area of A, E of A. And when I'm looking down here, it's the force in BD, length of BD, area of BD, and E of BD. Okay, and I cannot use the P that I get from each of these because I can't have all of these happening at once. This is the force that causes failure, force that causes failure, force that causes failure in each of these three scenarios. And the largest force I can put is 9.82, so that's what I have to put back on my system. And I use the 9.82 then to go through and figure out the forces in each cable. Okay, so I have that done. I know it's a lot of work, isn't it? It is a lot of work. So now what happens? So now I have to go back and I have to figure out all of my deltas. Okay, so I'm going to come back to this page, which has my information, and I need to find all of my deltas. So delta A equals, okay, delta A equals force of A, length of A, area of A, E of A, and my force in A was 3.68 kips. My length is 72 inches. My area is pi over 4.375 squared, and my modulus is 15,000 KSI. So units are all consistent. My delta C is force of C, length of C, area of C, E of C, and I get 6.1375 kips. My length of C, 92 inches. That's why it's so nice to have everything in consistent units. Pi over 4, D, 0.625 inches squared, and my modulus is 10,000 KSI. And then I can calculate delta D, which is the force in BD, length of BD, area of BD, E of BD, and I have 9.82. The length is 36 inches. Area is pi over 4, 1 inch, and then I have a modulus of 10,000 KSI. My units are all checking out. So if I multiply all of these things through and I do any of my math consistently, then I'm going to get 0.16 inches. I'm going down. I'm going to get 0.192 inches, and it's going down, and I'm getting 0.045 inches, and it's going down. Okay, so when I go back and look at my deformation, I have 0.192, 0.16. Okay, this has come down to B prime. And I have stretch here of 0.045. So now I have to go back and deal with this rotation because I have to figure out how far down we've come. So if this is 0.16, then this piece right here and this piece right here make up my triangles. And I have 2.5 and 1.5. So I have delta B minus delta A, delta C minus delta A, and now we can set up our ratios. Delta B minus delta A is to 2.5, as delta C minus delta A is to 2.5 plus 3, 4 is to 4, and delta B minus 0.16 is to 2.5, as delta C, 0.192 minus 0.16 is to 4. And when I do my cross multiplication, okay, I'm going to cross this over, divide, and then add 0.16. Delta B equals 0.18 inches, which makes sense. It should be somewhere 0.16 and 0.192. Okay, so I get 0.18 inches. So if I'm looking at the total displacement of point D, then it has to be B to B prime plus the delta of that cable BD. So I get 0.18 inches. That's from my rigid bar dropping and rotating. Okay. Plus 0.045 inches. That is from the stretch in the cable. And I get the total displacement is 0.225 inches down. Okay. And then the final thing it asked was the shear pin at B. So if I'm looking at B, I only have forces in the up and down. So I know that the shear of pin B has to equal that force that's in cable BD. So that was 9.82 kips. And I know that shear force equals V over A. Okay, so I have 9.82 kips over area, because that's what I'm trying to find. Okay, I've also been told that we have an ultimate shear strength of 70 and a factor of safety of 3, and we are in double shear. So I have an ultimate safety, or an ultimate shear of 70 KSI, and a factor of safety of 3. So this is my allowable over ultimate factor of safety, and that allowable is what my pin has to equal. It's also double shear, so I've doubled the area. So what is area? Pi over 4d squared. So I have 9.82 kips, that's my force, over 2 times pi over 4d squared, that's the area of a shear pin at B, equals 70 divided by 3 is 23.33 KSI. So I have units of kips, KSI, that'll give me inches. So when I work this out, okay, when I work through the algebra, I get that the diameter of my pin at C has to be greater than or equal to 0.517 inches. Okay, so it has to be larger than that. I'm not going to round down to 0.5. 0.5 is not big enough. I would have to round up to like 0.6. And there you have it.